So in part one, we talked about the tiny philosopher problem and different solutions to address and solve different problems like deadlock and starvation. And we also talked about different operating systems and their handling to concurrency mechanisms. And the second part of this week will be about memory management. So in this week, we start the introduction of the first component in memory management. If you remember, we talked about different managers that cooperate together and communicate within the operating system to provide the entire platform of different operating system. The second manager that which I would like to address in this week is the memory manager. In particular, I will talk about the basic requirement for memory management, including different techniques of memory partitioning. For next week, I will talk about the basic blocks of memory management, including paging and segmentation. So this topic, which is part of memory management, will be discussed over the next 2 weeks. So why um, why there is a need for memory management? One part for the operating system and one part for the program currently being executed. In multi-programming systems, the user part of the memory must be further subdivided to accommodate multiple processes, which is why we need to provide management for the memory. Because memory is cheap today and getting even cheaper, but on the same time, applications are demanding more and more memory. So there is never enough. Memory management would involve swapping blocks of data from secondary storage to the main memory and vice versa. Memory input output operations would be considered as a slow compared to a CPU operation, and the operating system must clearly identify or divide the time of the swapping processes to maximize the CPU efficiency. In a uniprogramming system, main memory actually is divided into two parts. One part for the operating system, which actually we consider information about the rhythm monitor and kernels, and the other part of the program currently being executed. And why the effectiveness of memory management would be clearly identified in multi-programming systems, such that if only a few processes are in memory, then for much of the time, all the processes will be waiting for input-output operations, and the processor will be idle. Thus, memory management need to be allocated in an efficient way to ensure a reasonable supply of ready processes to consume available processor time. Some of the key terms that we will uh, use a lot in memory management. So these are the memory management terms that from now on we will use them very frequently. The first one is called frame. So when I use the word frame, that means it's a fixed length block, but it resides in the main memory. When I use the word page, I'm talking about a fixed length block of data that reside in a secondary memory. It could be considered as disk, and a page of data may temporarily be copied into a frame of the main memory. Segment, on the other hand, is a variable length block of data that also reside in the secondary memory. An entire segment may temporarily be copied into an available region of the main memory. That's why we call it segmentation. Or the segment may be even divided into pages. Sometime later on in the class, in the lecture, you will see me talking about segments as a portion of multiple pages, such that it could be divided into pages, which can be individually copied into the main memory, not necessarily to be even in the same address or the same location in the main memory. And at this point, we are combining segmentation and paging philosophy. So if we are talking about the main memory, any fixed length block in the memory is called frame. If you are talking about the secondary memory, which might like, for example, like the hard disk. So any fixed length block of data is called page. If you have variable length block of data, will be called, so this is if we are talking about fixed lengths, if this is variable lengths, we will not call it page anymore, we will call it segment. While actually surveying the various mechanisms and policies associated with memory management, it is helpful to keep in mind the requirements that memory management is intended to satisfy. These requirements include the following. For any memory manager, there are certain requirements that the memory manager must satisfy, by which we guarantee that we have efficient allocation to processes into the main memory, and at the same time, efficient allocation of the processes to the processor. The main requirements include relocation, protection, sharing, logical organization, and physical organization. Let's now talk about each of those components separately. Starting by the first requirement of memory manager, which is relocation. In a multi-programming system, the available main memory is generally shared among a number of processes. Typically, it's not possible for the programmer to know in advance which other program will be present in the main memory at the time of execution of his or her program. In addition, we would like to be able to swap active processes in and out of main memory to maximize the processor utilization. And this could be done by providing a pool of ready processes to execute. Once a program is swapped out to the virtual memory like the disk, it would be quite limiting to specify that when actually would be the best time to swap it back into the main memory. It must be placed in the same main memory region as before. And instead, actually, we use relocation, which means we may need to relocate the process to a different area of memory, and this relocation would need addressing management. So we can't know ahead of time where a program will be placed. And we must allow for the possibility that the program may be moved about in the main memory due to swapping processes. These facts raise some technical concerns related to addressing, as we can see in the following figure. This figure actually shows a process image. For simplicity, let's assume that the process image occupies a continuous region of a main memory, like it occupies a continuous number of frames in the main memory. Clearly, the operating system will need to know the location of the process control information and of the execution stack, as well as the entry point to begin execution. So we need this information is stored in the process control information, in which we need to identify the entry point of the program, as well as the information about the execution stack, which we need to store the current top address of the stack. Because the operating system is managing memory and is responsible for bringing this process into main memory, these addresses are easily to come by. In addition, you should be aware of that the processor must deal with memory references within the program. So if we do have branch instructions, we know that those branch instructions will contain an address to reference the instruction to be executed next, which is handled by the processor. Data references instructions would contain the address of the byte or word of the data references. Somehow, the processor hardware and operating system software must be able to translate the memory references found in the code of the program into actual physical memory addresses. So when we use the word physical address, we refer to actual address in the main memory. Why do we need to do such translation? So they can reflect the current relocation of the program in the main memory. So that's why the idea of relocation came from. When you remove one process from the main memory and then you put it into the virtual memory, and then at some point this process is ready to be executed, then you have to take it back and put it into the main memory. So all the addresses, the start address of the process and the end address of the process, as well as allocation of the start point of the stack and the execution processes within the process, should be restored or relocated. The second requirement for memory management is protection. Each process should be protected against unwanted interference by other processes. Whether these interferences could be accidental or even intentional. Thus, that means programs in other procedures should not be able to reference memory location in a process for reading or writing purposes without permission. In one sense, satisfaction of the relocation requirement would increase the difficulty of satisfying the protection requirement, because when you return a process back into the main memory and then you would like to relocate the addresses of the processes, you may actually overcome some of the memory locations assigned to other processes. So how would you um, um, guarantee the protection and as the relocation at the same time? The reason for this hard task is because the location of a program in main memory is unpredictable, and it's impossible to check absolute addresses at the compilation time to assure protection. In addition, most actually programming languages, they allow the dynamic calculation of addresses at the runtime, not the compilation time, which make it even hard. That means all the memory references generated by a process must be checked at the runtime to ensure that they refer only to the memory space allocated to that process. Fortunately, we shall see that different mechanisms are used to support relocation, would also support the protection requirement in different operating systems. Normally, a user process can't access any portion of the operating system, neither program or nor data. Again, usually a program in one process cannot branch to a given instruction in another process. And actually, without special arrangement, a program in one process cannot even access the data area of another process. The processor must be able to abort such instructions at the point of execution. You just need to keep in mind that the memory protection requirement must be satisfied by the processor. That means it is done on the hardware level rather than on the software level. And this is mainly because the operating system can't anticipate all of the memory references that a program will make. Even if such anticipation were possible, it would be prohibited to guarantee an efficient time management, because at this point we're consuming time to screen each program in advance for possible memory reference violations. It is not only possible to assess the permission of a memory reference, or whether it's data access or even a branch instruction at the time of execution of a given instruction, that will allow future references. It's really hard task. So that's why the processor, hardware level, should be assigned such task. The third requirement in memory management, which is sharing requirement, any protection mechanism must have the flexibility to allow several processes to access the same portion of the main memory. So now there's a contradiction between protection and sharing. So an efficient memory manager should allow protection to location in the main memory for certain processes, and at the same time allow sharing between processes who would like to communicate over a shared resource. For example, if a number of processes are executing the same program, it is actually very good to allow each process to access the same copy of the program rather than have its own separate copy of that program. Processes that are cooperating on some task may need to share access to the same data structure. And also the memory management system must therefore allow controlled access to shared area of memory without actually compromising essential protection. That's why I said that an efficient operating memory manager should actually handle both requirements, including protection and sharing. Again, we will see different mechanisms that are used to support relocation, would also support sharing capabilities. and even protection capabilities in different operating systems. So in order to support the relocation and the sharing mechanism, we have to talk about logical organization versus physical organization. So for logical organization, memory is organized as linear array. Um, Sometimes we look to the main memory in a computer system as a one-dimensional address space. So you look to one-dimensional address space or one memory consisting of a sequence of bytes or words. And second memory at its physical level is similarly organized. So like we look to both of them are just like one-dimensional address space where all bytes or words are listed in sequence. However, for the secondary memory, keep in mind that the organization of the one-dimensional array would actually mirrors the actual machine hardware implementation. It doesn't correspond to the way in which programs are actually typically constructed, but somehow we organize it in such sequence so it makes the memory management in the secondary memory more accessible. Most programs are organized into modules, some of which are unmodifiable. So that means it only allowed read and it doesn't allow write. And some of which will contain data that may be modified. If the operating system and computer hardware can effectively deal with user programs and data in the form of modules of some sort, then a number of advantages could actually be realized, including modules can be read and compiled independently, with all references from one module to another module could be resolved by a system at the runtime. Also, with modest additional overhead, different degrees of protection, like read only, execute only, can be given to different modules. It is also possible to introduce mechanisms by which modules can be shared among processes to advantage of providing sharing on a module level that is would correspond to the user's way of viewing the problem, and hence it could make it easy for the processes and user processes to specify the sharing that is desired. As a matter of fact, the tool that is most readily satisfy these requirements for logical organization is segmentation, which is one of the main memory management techniques that will be explored later. So when we refer to logical organization of the memory, we're just referring to one dimension array in which all the frames are listed in sequence. And each frame has a memory, a physical memory address. On the other hand, um, um, each frame in the main memory has a physical memory address, and each program or a pseudocode, they will have a logical address. As we discussed before, for main memory provide fast access at relatively high cost. In addition, main memory is volatile, which means that it doesn't provide permanent storage. Um, on the other hand, secondary memory is slower and cheaper than main memory and is usually not volatile. So that means that the second memory of large capacity can be provided for long-term storage of programs and data, while a smaller main memory holds programs and data that are currently in use. In this two-level scheme between alternating between the main memory and the second memory, the organization of the flow of information between main and second memory is a major system concern. The responsibility of this flow could be assigned to individual programmer, but this is impractical and undesirable for two main reasons. The main memory is available for a program, plus its data may be insufficient. In that case, the programmer must engage in a practice known as overlay, in which the program and data are organized in such a way that various modules can be assigned the same region of memory, with the main program responsible for switching the modules in and out as needed. Even with the aid of computer tools, overlay programming wastes the programmer time. In the multi-programming environment, the programmer doesn't know the time of coding and even how much space will be available or where that space would be. It is clear that the task of moving information between the two levels of memory should be a system responsibility. This task of memory management component. The principal operation of memory management is to bring processes into main memory for execution by the processor. In almost all modern multi-programming systems, this would involve a sophisticated scheme which is known as virtual memory. Virtual memory is in turn based on the use of one or both of two basic techniques like segmentation and paging. And before we can even look at these virtual memory techniques, we must prepare the ground by looking at simpler techniques that do not involve virtual memory. So how are we going to address this in terms of memory management? We first assume that there is no virtual memory and see which techniques are commonly used to provide efficient memory management, including partitioning techniques. And then once we start talking about virtual memory, we will talk about the most commonly used techniques for virtual memory, which includes paging and segmentation. Among all the techniques that are used to provide support for memory management without the involvement of the virtual memory is partitioning, which has been used in several variations. In some, now we call it obsolete operating systems, so they are not used anymore. However, the other two techniques like simple paging and simple segmentations are not used by themselves. However, it will clarify the discussion of virtual memory if we look first at these two conditions in the absence of virtual memory considerations. So how are we going to do it? As I said, we're going to assume that we don't have virtual memory. So we're going to talk about partitioning, and we can even address paging and segmentation without virtual memory involvement. And then we will talk about paging and segmentation when virtual memory is involved. So the following table provides a summarization of different memory management techniques, including partitioning, paging, and segmentation. For partitioning, we have two types. The first one is the fixed partitioning, and the second one is dynamic partitioning. And for paging, we do have simple paging where no virtual memory exists, and then we have virtual memory paging. And for segmentation, we have simple segmentation where we don't have any virtual memory involved, and then virtual memory segmentation. For fixed partitioning, so this is a way of optimizing the usage of the main memory in a way that main memory is divided into a number of fixed size partitions, and they are divided at the system generation time. A process may be loaded into a partition. This partition is of equal or greater size. The strength of this fixed partitioning method is that it is simple to be implemented. It is commonly used in many operating systems in the old ages, and it needs little operating system overhead. However, it suffers from insufficient use of memory due to internal fragmentation. So we're going to talk about two different problems now when it comes to partitioning. The first one is called internal fragmentation, and the other one is called external fragmentation. So internal fragmentation means we have fragmentation within the partition, and external fragmentation means we have fragmentation outside the partition. Also, one of the disadvantages of fixed partitioning is that maximum number of active processes is fixed. On the other hand, dynamic partitioning allows the creation of partitions in a dynamic way so that each process is loaded into a partition of exactly the same size as that process. One of the good things about it, strengths with dynamic partitioning, is there is no internal fragmentation within the partition, which means it will have more efficient use of the main memory. However, it doesn't use the processor very efficiently. This is mainly due to the need for compaction to counter external fragmentation. So we don't have internal fragmentation, but with dynamic partitioning, we do have external fragmentation. I will talk about these two behaviors in the following slides. For sample paging and sample segmentation and virtual memory paging or even virtual memory segmentation, I will leave this for now. I will talk about them in more details when it comes to paging and segmentation, whether it's on the main memory level or the virtual memory level. So in most schemes for memory management, we can assume that the operating system occupies. So this is where the operating system will occupy some fixed portion of the main memory. And the rest of the memory is available for use by multiple processes. The sample scheme for managing this available memory is to partition into region with fixed boundaries. This is the first simple way. Where for partitioning, it could be partitioned with equal size partitions or unequal size partition. So for fixed partitioning, which means that we do have the main memory divided into a number of static partition at the system generation time. It could be either of fixed size or it could be either of unequal size. One possibility is to make use of equal size partition. And in this case, you can see all the memory partition are of the same size. So it is 8. All of the partitions are of 8 megabyte. There is no unequal sizes of partitions. So this is where we call it is fixed. However, it could be unequal sizes, it's still fixed, but it could be size 2, or it could be size 4, could be size 6, or 8, or even 12, or even 16. Still fixed partitioning of the memory, and it's done at the generation time, but it could be equal or unequal sizes. If we do have it on equal sizes partitioning, in this case, any process that will of size that is less than or equal to the partition size, it could be easily loaded into any available partition. So assume now I have a process 1 of size 4 megabyte, and we assume that we scan the memory from the top to the bottom, and then the process maybe will reside on the first partition over here. So this is where the process 1 will reside. So you can see that we have fragmentation within the partition. Like now we have another 4 megabyte that are not used. So this is what we call it internal fragmentation. So internal fragmentation is fragmentations within the partition. If all partitions are full and no process is in the ready or running state, the operating system can swap a process out of any of those partitions and load in another process. So there is some work for the processor to do. We can see that for equal size partitions, if a process is of size 4, it would go, it is more suited to be in here. That means we don't have a lot of internal fragmentations. We still might have a process, assume I do have a process of 5 megabyte, so it will reside on the second partition, and then I will have 1 megabyte of internal fragmentation. So we might still see internal fragmentations. So this is 1 megabyte of internal fragmentation, because at this point we have fixed partitioning, whether of the same size or not, but it's fixed. Like the memory has been pre-partitioned before even the processes are created or arrived. We see a lot of internal fragmentations with fixed partitioning as compared to dynamic partitioning. There are two main challenges with the usage of equal size fixed partitioning, is that a program may be too big to fit in a partition. So in this case, the programmer must design the program with the use of overlays so that only a portion of the program need to be in main memory, at any one time when a module is needed, which is in the current state not available. The user program must load that module into the program partition and overlaying whatever programs or data are there. Another problem is we might have a situation where the main memory utilization is extremely inefficient, which might see a scenario where any program, no matter how small, would occupy an entire partition. In our example here, we might see that there may be a program that has a length of less than even 2 megabyte, and it could occupy an 8 megabyte. Keep in mind, scanning of memory goes from top to bottom. So even we have a fixed size partition of 8 megabyte, and then we have a process or a program of just 1 megabyte size, it will still occupy the partition and no other process can occupy the partition. So that means we do have a fragmentation inside the partition. And this phenomenon, which actually has a wasted space internal to a partition due to the fact that the block of the data loaded is smaller than the partition, is called internal fragmentation. So with equal size partitions, the placement of processes in memory is trivial. As long as there is any available partition, a process can be loaded into that partition. Because all partitions are of equal sizes, it doesn't matter which partition to be used. If all partitions are occupied with processes that are not ready to run, then one of these processes must be swapped out to make room for a new process. Which one to swap out is a scheduling decision. And actually, this scheduling decision, we have addressed it before in terms of queuing management. And if a process has a priority, then it could immediately be scheduled to the processor. And if the scheme of scheduling is first in, first out, so if it has been swapped out at time t, then it will not be entered into the execution state until it has been released from the queue. So with unequal size partitions, on the other hand, but we're still talking about fixed partitioning placement, there are two possible ways to assign processes to partitions. The simple way is to assign each process to the smallest partition within which it will fit. In this case, a scheduling queue is needed for each partition. To hold swap out processes that are designated to that partition. The advantage of this approach is that processes are always assigned in such a way to minimize wasted memory within a partition, which means would minimize the internal fragmentation. Although this technique seems optimal from the point of view of an individual partition, however, is not optimal from the point of view of the system as a whole. As you can see in the second figure, consider a case in which there are no processes with size between 12 and 16 at a certain time. In that case, the 16, so if this is a 2, like let's go back to the partitioning. If this is a 2 megabyte and this is a 4 and this is a 6, 8, another 8, and then 12, and then 16. And now if you assume that we don't have two processes that are of size 12 or even 16 megabyte at a certain point of time, at this point, the 16 megabyte partition will remain unused, even though some smaller processes could have assigned to it. So at this case, a preferable approach would be, instead of using multiple queues to each partition, would be to use a single queue for all the processes. When it's time to load a process into a main memory, the smallest available partition that will hold the process is selected. This is the best optimum strategy. If all the partitions are occupied, Then a swapping decision must be made, and the preference might be given to swapping out the smallest partition that would hold the incoming process. It also possible to consider other factors such as priority, as I said before, and a preference of swapping out blocked processes versus ready processes. So the use of unequal partitions would provide a degree of flexibility compared to fixed size partitioning. In addition, it can be said that fixed partitioning schemes are relatively simple and require minimum operating system software and processing overhead. However, it suffers from the following disadvantages. The first one, the number of partitions specified at system generation time would limit the number of active processes in the system. Also, because partition sizes are present at the system generation time, small jobs will not utilize partition space efficiently, and this will cause internal fragmentation. In some environments where the main storage requirement of all jobs is known beforehand, this may be reasonable, but this is not happening in most cases. And actually, it is an inefficient technique. That's why dynamic partitioning is provided. To overcome some of the main drawbacks with fixed partitioning, an approach which is known as dynamic partitioning was developed. Again, this approach has been uh, provided to, however, it has more sophisticated memory management handling techniques. An important operating system that used this technique was the IBM mainframe operating system, which supports multi-programming with a variable number of tasks. With dynamic partitioning, the partitions are of variable length in number. When a process is brought into the main memory, it is allocated exactly as much memory as it requires and no more. That means we don't have internal fragmentations, because internal fragmentation means that we do have which was related to fixed partitioning, where the memory is already partitioned, whether it's equal size or unequal size. The memory is pre-partitioned, and then when processes arrive, they will look into the partitioning, and each process will go to the best fit partition. In dynamic partitioning, this is not the case. The dynamic partitioning, each process will be assigned to exactly the same size it is required. Now let's take the following example. So using a 64 megabytes of main memory is shown in this graph, in this figure, where we have 8 megabytes allocated for the operating system, and then we have a 56 megabyte allocation for user processes. Initially, the main memory is empty, except where, as I said, the operating system is loaded. And then the first 3 processes are loaded in, starting where the operating system ends and occupying just enough space for each process. So the first process is of size is process 1 and process 2, and then process 3. So process 1 would need 20 megabyte, and then process 2 would need 14 megabyte, and then process 3 would need 18 megabytes. So if they will be allocated exactly to the space that they are requesting, you can see that there is no internal fragmentation within process 1. It requested 20 megabytes and it was allocated to 20 megabytes. And then in a sequence of allocation, we assume process 2 just reside immediately after process 1. So that means the next 14 megabyte will be allocated in the main memory after the first 20 megabyte. And then the third one will reside after process 3, will reside after process 2. So that means we have another 18 megabyte. This actually will leave a hole at the end of the main memory. So we do have another 4 megabyte. That is too small for a fourth process to be allocated. At some point, none of the processes in the main memory is ready. So the operating system will swap out some processes, that would free some parts of the main memory. Um, those main memory free spaces will leave sufficient room to load new processes that would need a place to reside in. So now if you assume that the operating system would decide which process to leave, and then with the assumption that it was process 2, so that means we do have 14 megabyte of free space that was allocated by process 2, and then process 4 arrived that would need another 8 megabyte. And because process 4 is smaller than process 2, so we have another hole. Later, a point is reached at which none of the processes in the main memory is ready, but process 2 is now in the ready suspended state, which make it available. And process 2, because there is no sufficient memory in the memory for process 2, the operating system would need to swap out some other processes, and then maybe the decision was for process 1. These are just assumptions for this example. And then process 2 will swap back. So process 2 will find the first spot that need only for 14 megabyte. So we can see that we now have another fragment. So now we have 3 holes within the memory, not within the partition. So this example actually addresses a phenomenon or a behavior in which we have a lot of small holes in the memory. As time goes on and memory allocation is scheduled in this way using dynamic partitioning, we will see that memory becomes more and more fragmented and memory utilization would decline. This phenomenon is referred to as external fragmentation. So these behaviors where you see small holes within the main memory, not within the partition, is called external fragmentation. So external fragmentation is very commonly used with dynamic partitioning, while internal fragmentation is commonly used with fixed partitioning. Internal fragmentation would indicate that the memory that is external to all the partition become increasingly fragmented. This is different when we compare it to internal fragmentation, which is a problem associated with fixed partitioning. So dynamic partitioning has caused external fragmentation, while fixed partitioning has caused internal fragmentation. One way actual to solve the dynamic partitioning problem is called compaction. So from time to time, the operating system would shift the processes so that they are continuous, like in sequence, and so that all of the free memory is together in one block. So for example, if we go back to the previous example here, what will happen is after we have the status in the H situation, the operating system will shift process 4 to start immediately after process 2 and process 3 to start immediately after process 4. So we will have at the end, instead of 4 megabyte, we will have the 6 megabyte added to another 6 megabyte. And then we, with 4 megabytes, so instead of having 3 blocks of different sizes, we will have a big 16 megabyte block that would fit an incoming process. So compaction is all about shifting processes so they are in one sequence or in a serial location. This may be well sufficient to load an additional process. However, the difficulty for compaction is that it's real-time consuming procedure and wasteful of processor time, because every time this has to be done to guarantee that we have bigger sizes fragments. This is a timing consuming process. That means it must be possible to move a program from one region to another in the main memory without actually invalidating the memory reference in the program, because compaction would causes a lot of wasting of time. This process would need a lot of monitoring or handling. So compaction implies the need for a dynamic relocation capability, which is another overhead that will be added to the system. And because such thing will cause memory management to be time consuming, the operating system designer must be clever in deciding how to assign processes to memory, how to plug the hole, or how to fill in those holes. When it's time to load or even swap a process into main memory, and if there is more than one free block of memory of sufficient size, then the operating system must decide which free block to allocate. Next class, we will talk about placement algorithms. So this, I will stop here, and then next class, we will talk about placement algorithms that might be considered to enable efficient memory allocation and to overcome the memory compaction solution. And instead of just fitting and then compacting, maybe you should place the processes in a way that could be either best fit or first fit or next fit strategy. So I'll talk about these placement algorithms in the next class for next week. And with this, I'm ending this week material, and I will see you next week. Thanks for listening.